Ladies and gentlemen, I'm very happy to contribute again to the GiD Convention 2022. I'll be talking about GiD interface to our software ATENA, which is devoted to the modeling of reinforced concrete structures. And more specifically, I'll be focusing on 3D concrete printing or modeling of 3D concrete printing, which is a new feature in ATENA software. A few words at the beginning, maybe I should say about our company. We are located in Prague, Czech Republic. We are a small company with about 20 engineers, most of them highly qualified with PhD degrees from international universities. And although small company, we are very active internationally with distributors all over the world and consulting projects in United States, Europe, Asia, India, and so on. So what do we deal with? So we develop technology and software for nonlinear modeling of structures, such as those that you can see on the slide. That means bridges, nuclear containments. Nowadays, with this wind energy, offshore structures is a very popular topic. Well, a few words about our software. This slide describes the three main unique features. First one is that we can nicely and in a very detailed way model the reinforcement. If needed, each reinforcement can be taken into account in our model. We have a very realistic post-processing and visualization of the cracks that typically develop in concrete structures. And the last, but very important and very useful feature, unique feature in our software is the possibility to see what's going on even during the analysis. This screen on the left bottom shows a typical view when you run our software. So you can set up some monitors, you see how the structure deforms, how the load displacement diagram is developing. You can see how the structure cracks, and so on, deforms. So basically full post-processing is available when the program is running. That's why we like to call it virtual testing, when like you are testing your structure in a laboratory, but this time the laboratory is your computer. Summary of material models. So of course our main material on which we are focusing is concrete. So we have a material model for concrete which combines fracturing part with the plasticity based model to capture concrete crushing. For soil and rock we have a Drucker-Prager model. For another interesting model, we have a very unique model developed by Professor Bajant, microplane model called M7. For steel, we have von Mises model. It is also interesting to know that we have time-dependent models, not only for stress analysis, but also for transport problems, such as heat analysis or moisture. In addition, we can simulate long-term behavior of concrete structures, such as creep, shrinkage. And recently, we developed also models for durability. That means mainly for reinforced concrete, it is a problem of corrosion. So why nonlinear analysis is important and useful in practice? That's because it provides a very good understanding into the structural behavior. The engineers can really understand what is the maintenance, what is the failure mode, and ultimate load carrying capacity. Of course, we should understand that this is not a replacement of the standard engineering tools or engineering judgment, but I like to emphasize that our ATENA software is a supplement to these standard engineering tools, which is a very good way how to check the design. And why we need to do that? This is because typically our design formulas are based on laboratory experiments of beams typically, or small specimens, or plates, slabs, or basically small specimens. And now we need to extend this to, in practice, we often need to model situations like this, where we have some concrete, for instance, some steel embedded into concrete, or we have a very fancy architectural designs, like this Expo Pavilion of UAE, or we have now this 3D printing, which is a very new technology, and the standard tools from that we use, that we have in the codes, is not usable here anymore. So, small summary of what we use. The main method we are using is finite element method. We are using a smeared crack formulation with crack band model. That means inside our finite elements, we are using nonlinear material models. And then our analysis follows in an incremental way in this predictor-corrector approach. This is a summary, brief summary of our concrete material model. So we are, as I told you before, we have this Rankine-based softening model for concrete in tension, and in compression we have this 3D criterion implemented in a plasticity-based model with hardening and softening. Both softening in tension as well as in compression is based on energy or fracture mechanics concept, so that the proper energy is dissipated independently of the finite element size. To model reinforced concrete, we of course need additional elements or features to model reinforcement interfaces, and we have two reinforcement models: discrete one, where we have embedded bars inside our finite elements, or a smeared one, when basically the reinforcement is like simulated with a composite material consisting of concrete and reinforcement in certain directions. To model various pre-stressing tendons, such as the external cable, we have also special features for that. Now I would like to show a small example, or one example. It's not so small actually. This comes from a nuclear industry. We participated in some assessment, seismic assessment of various buildings in this nuclear power plant, starting from the reactor building with the various buildings inside the power plant, important buildings, because they, for instance, this building E was housing the control room for the power plant. This slide kind of summarizes the concepts that we can use when modeling these relatively complex structures. So we have a 3D model of the whole building, and we use two models of the reinforcement. The critical reinforcement in the beams and columns is modeled with this discrete approach, where each reinforcement is modeled inside our numerical model. But the reinforcement in the walls and in the slabs is useful to model by this in this smeared way. Here you see some results from pushover analysis in y direction, plus y and minus y. On the top right, you see the stresses in the discrete reinforcement. At the bottom, you see the strains in the smeared reinforcement. Here are on the left are the calculated pushover curves, and on the right now I'm showing an animation of such a typical analysis, showing the deformed shapes, the crack pattern as it develops, and the colors are indicating the crack width. So you see the cracks are developing. We nicely see the shear failure, and then after the peak, you will see the collapse of the columns. The largest cracks are now indicated by this red color. Well, now I would like to mention one of the latest features in ATENA. That is the modeling of 3D printing. And well, why do we want to do that? Why do we need a simulation? Well, in this 3D printing, very often you see this situation because when the printing speed is very fast, the concrete is very fresh. When you are modeling some inclined walls, you may end with a collapse of your structure and you end up with a pile of fresh concrete. So this is, of course, usually not a problem nowadays because they are printing rather small structures. But you can imagine if it starts to be used, this technology, for something more serious, and you have a collapse. First of all, it may be quite a waste of materials. In addition, somebody might be injured or some equipment may be damaged. So let me show what input we have in our GiD interface. So there are several important parts. One is the definition of material properties, and then we need to define the printing process. How the process works is that we create our finite element model in GiD, and then we define the material properties. In this case, we have to consider the fact that the concrete will be quite fresh when it is printed. So we need to input the time-dependent relationships for the important material properties, such as elastic modulus, compressive, tensile strength, fracture energy, and so on. So this must be provided as an input to the analysis. And then in in the interval data, as you know, in GiD, we have a special dialog to define these digital printing properties. It is called DigiCon in ATENA. And there we need to define the time increments, the time which is involved in the printing process. And important is that we need to define now the path. And this path can be either defined by this CSV file, which contains the trajectory of the printing head. But we are now also extending this, that as an input, it can take the G code. For those of you who don't know, the G code is the typical language that is being used by this machine, which is used for 3D printing. So this shows how the trajectory is defined, and then depending on the layer, speed of printing, the individual finite elements will be activated with different age. Of course, they will activate their self-weight, and in addition, for instance, the shrinkage can be considered. So the construction process is then defined by this printing path, printing starting time. We can have some interruptions. We can even optimize the track. There may be some delays. So all this can be provided. And let me show you now some video of one case which was part of this project, which we did in cooperation with the University of Dresden, where they were printing this sample house. Well, you may be surprised that in this case there are sharp corners. Typically in the 3D printed structures we see curved shapes, but in this project there was a special objective to develop the printing head that can print sharp corners. And if this analysis shows this situation when the printing speed is selected too fast, and after reaching certain height, we observe elastic buckling or viscoelastic buckling of the walls, which is a very typical situation The collapse usually is not because of reaching the compressor, the strength of the material, but often it is due to the viscoelastic buckling. So in this case, the wall collapses at the height of about 1 meter. But if we reduce the printing speed, of course, the whole building can be printed. So with this, I would like to conclude my presentation. So we have this, we are using GiD as a preprocessor to our ATENA software, which is focused on modeling and simulation of concrete and reinforced concrete structures. And I emphasized in my presentation the application or recent extension of our software to the modeling or to the simulation of 3D printing of concrete. So thank you very much for your attention, and goodbye.